there's the first group of code, which is the initial uh, conditions for the example.
Yep. Parameter real k equals that one,
Yeah,
right?
yeah, and then you just put in everything from the examples into there. So K equals 0.5 watts per meter per watt. You just put it in there, and then define A is what, Q is what, L is what, and so on and so forth until all parameters are in there. And then there's one parameter missing for 4.2, which is
Q.
Q.
Yep.
You just copy it like the rest, paste it in, change
Yep.
the Q into the value that is in the example. And then the text below we can ignore. Del X is just what's already given in the example, which is just like the first one. I think we're gonna change. Oh no, here it is. It's in solution. Under solution, there's this the first paragraph del x equals 0.004, and then that's what that is. And then we jump into equations. The code under equations. From that, you scroll down to where there's the table with all the equations. That is under boundary node one.
Yep. See.
Yeah, there's a table with two rows, right?
Yep.
Nah.
Two columns.
Yeah. So what's under those what's it called? What's under those parameters? AW, AE, SP, SU, and AP. We fill in exactly as it is on the table. So AW is equal to 0, so we put 0 next to AW1 equals yada yada, and then
Yep.
AE we fill in K times X per del X. We literally put del X because we define del X as that. And then you fill in everything until all is filled, and that'll be for boundary node 1, which is the first one, where there's the 1 in the close brackets. We go back to equation 4.30, and no, sorry. We first so here's the deal. These equations, these sets of equations, the first, the second, and the third, they are defining what equations are for which node in the diagram.
Hmm.
So AW1 and so on is referring to the equations at node 1. AWN and so on, it refers to the equations at node 5.
Okay.
And then for the next one, where AWI for I in 2 is n minus 1.
Wait. AWI. Where is it?
In the code, it should be below AWN.
Oh, AWI.
Yeah, yeah, yeah. Uh, those equations refer to nodal points 2, 3, and 4, which is not defined as node 1 and node 5.
Okay.
So,
Got it. So the equations on top is for node 1 and 5. The ones on the bottom is for nodes 2, 3, 4.
yes. And then in the example, they already gave us for nodes 1, 5, and 2, 3, 4. So we just fill in as is in the book into the program.
Okay.
And then below that, uh, it's just defining the temperature at TW, which is the first node.
Is that given in 4.12 and
Yeah, that is given. So
okay.
that is the initial temperatures that is given. Like in example 4.2, they give us two walls, right?
Yep.
And they gave us TA and TB, which is the two initial temperatures of those walls. TA is the initial temperature of wall A, and TB is the initial temperature of wall B.
Yep. Yep.
Now, TW is the temperature at the most west node. which is why it's called TW. And TE is for the one in the east, where the west is on the left hand and the east is on the right hand. Just like that. It's not really something that is constant. It's just we define it ourselves.
Oh, so what do you write TW
Uh,
equals?
TW is TA and TE is TB. So TW equals 100, TE equals 200, and then the TE1 equals TP2, and the one below it is just as is. It's the looping of the code itself.
Okay. Okay, after that?
Okay, after that, uh, the next one is also for looping, so we can skip that. Where TW, where in there's the I in the brackets.
Yep, yep,
Yeah, we can just skip that because that's gonna be constant. And then for the
yep,
last one, for these two untitled equations and the one for the next one, that we go back to the example. Let's say for the first one, AP1 times TP1, we go back to equation 4.33, and that
okay.
is the discretized equation for boundary node 1 where APTP equals AWTW
Yep,
plus AETE plus SU. So we just directly copy that in there.
yep,
Same for all the other nodes. So just like the other one, AP1 is for node 1, APN is for node N, which is node 5, we defined at the start, and API is for the ones in between.
yep,
Okay, after you put all that in, we'll just check the code with the green check mark and the green circle. And then a pop-up should
okay,
pop up. It should include 3 lines where it has been completed successfully. The amount of equations and variables should be identified and how many of those are trivial equations. And after that, right next to those group, there's the green arrow, which is by itself, just a green arrow. It says simulate, and then we simulate that. Just click and wait for it
yep,
to be done. And when it's done, we should expect a graph to pop up. Just an empty graph, no lines yet, because we haven't selected which lines to be viewed. So after the graph is enabled, we click on the checkbox next to TP so that we can see the graph. And we can see the values that is right here for us. And we can verify that those values are the same as the book if it allows me. Let's scroll down and here. So T1 is 150, T2 is 218, T3 is 254, T4 is 258, and T5 is 230, which is exactly the same as the one in the book. Now, why is the graph looking like this? Well, from the example, we know that there is a uniform heat generation of Q equals 1000 kilowatt per meters cubed, which means there is a uniform heat generation in the wall itself. And because of that, the heat goes up generally. However, the one in the left hand side is lower in temperature when compared to the one on the right hand side, as it is already um, defined in the problem where TA, or the one on the left hand side, is 100 and TB is 200, which is the one on the right hand side. And we can see that the increase in temperature reflects on these values, which is why, which is also why the peak is not exactly at the middle, but more towards the right hand side. To example 4.3, it's going to be nearly identical to the one in example 4.2, where we define all our parameters, our initial parameters in the start, just like in the book where n is equal to this, and then we take the square root of this, which we get 5, uh, and then the length is 1 as in the book. T ambient, or the ambient temperature, will be in 20, and then the base temperature of the object, which is this diagram, is at 100, and the initial temperature will be 0, so there's nothing affecting our system, and the number of control volumes will be 5. This is exactly like example 4.2, and then this is just to uh, moving on, and then just like example 4.2, we uh, we put in the equations, the general equations of each uh, parameters into this software, where in the node 1 and node 5 will be like this for node 1 and this for node 5, and for those in between will be following in this, an example 4.46, and then we define the initial temperatures in the westward diagram, which is right here, and the easternward. So this is going to be the base temperature, and this is where the ambient temperature is going to be, and then we define the temperatures for in between those 2 points that we just defined, and then we put in the general form of the equation into here for software to use. Then after that we check if it's all okay and simulate, and then we wait for simulation, and once the simulation is done we will be able to see a graph which is empty, and because I tested before, the graph is not empty. It'll show the checkmark line that we want to see. If it were like the start, it would be like this, and then we just have to check here, and to verify if the results given is identical to the book, we can do that by going in here, right here. So T1 is 64.22, T2 is 36.91, T3 is 26.5, T4 is 22.60, T5 is 21.30, which is identical to the book over here. And why is the diagram showing us these values? Why do these values show up in the chart? Well, if you look in the diagram, where this is going to be the base temperature and this is the ambient temperature, we can see that surely there's going to be temperature change from here all the way to the ambient temperature, but in the end there is convection. There's convection going through this uh, system right now. So as we go along down to the eastward side of the diagram, the temperature will be the same as the ambient temperature, unlike the one in the westward side where there is a base temperature set and there's going to be a difference in the rate where convection takes away the heat and makes it the same as the ambient temperature.